Welcome. Today's notes worksheet is entitled Rational Equations. We've had some experience manipulating and performing operations on rational expressions. Now we get the opportunity to solve equations in this particular family. So why don't we go ahead and dive right in and take a look at the example 1 at the top of your page, see what concepts we can develop and see what applications are out there as well. So the example 1 states, what value or values cannot be substituted in place of x? So what I have here is just two very simple rational expressions, one right here of course, and one right here. And what's the one thing we need to be concerned about when dealing with a fraction? What would be the one value of x that I would have to exclude in this particular case right here? Well, as we all know, numerically, the only thing I need to be concerned about in a fraction is dividing by 0. And so if I have an x value of 1, this does not work numerically. It would be undefined. And so all you need to do for right now is just write the fact that we can't have an x value of 1. X can be any other value here, and I would be able to perform this operation. If x is 1, very simply it's undefined. And as I move over to letter B, the numerator's all right. I don't mind having 0 in the numerator. 0 divided by anything is going to be 0. But of course I do have the issue of being 0 in the denominator. And so as a result here, I'm hoping you would agree with me that if x was -6, we would simply not be able to perform that calculation. That would be an undefined situation. And so as a result, x can be any number here except for -6. And so what we want to do as we solve these equations, we do need to be cognizant of that fact. We need to be aware that if we get an answer that would make the denominator 0, well, in essence, it simply wouldn't work. All right, so there are going to be two types of rational equations that we're going to investigate here today. The first one is probably pretty straightforward for our purposes here. So let me just go ahead and read it and take a look at the example and the strategy and then go forward to the next one. So it says the first type has one rational expression set equal to a second rational expression. This happens to be what is called a proportion. And you've probably had a lot of experience in Algebra 1 and geometry as well. I'm just kind of solving these types of rational equations right here. One set equal to another. And if you remember how we pull this off, we very simply cross multiply. This times this is the same as this times this. There's a lot of proportional reasoning that you probably did in Algebra 1, and there are a lot of geometry theorems and formulas that kind of go and produce these types of equations. So again, I'm pretty sure you've had that background, and we will go ahead and at least do one with that cross multiplying. But there is a second one that we're going to go ahead and take a look at that is a little bit harder, and there are probably a couple ways to pull it off. I'm going to try to show you what I would consider the slightly shorter way and more efficient as well. So number 2, the second type has more than one rational expression on a particular side of the equation. And of course, as you can see, here's the example right here. In this case, the right-hand side is the sum of two rational expressions, something like that right there. So we can't just go ahead and cross multiply here. Now, I will go ahead and read the strategy over on the other side in just a second, but I'm hoping you would agree with me that maybe a more formal approach would be that we can add these two rational expressions together and combine them into one fraction. And once we combine them into one fraction, then we could probably go ahead and cross multiply. So that's the alternative. If you don't like my more efficient, in my opinion, strategy, which we'll talk about right here, if you don't like it, again, what I would say formally, what you can do is just add or subtract, basically combine these two fractions together and then cross multiply. But what we're going to do here is very simply this. We're going to multiply every term in the equation, each fraction essentially, by the least common denominator. And so I'm going to multiply the left-hand side of an equation by the least common denominator, and I'm going to multiply the right-hand side of the equation by the least common denominator. And notice, of course, why there's a question here, sort of asking why we can do this. So it does say, why can we do this in the equation? And let me go ahead and just write down what I have on my sheet, and you can copy it in, and then we'll give it a try. So basically what we're going to do, as it says, is multiply each side by the LCD. And remember, multiplying both sides of an equation, and that's the idea, got to do both sides. So multiplying both sides of an equation by the same term, whatever it may be. In this case, I'm specifying that it has to be the LCD. But multiplying both sides of an equation by the same term very simply still keeps it in balance. And that's what we want. We're going to change the form without changing any of the values. And as long as I balance everything out, whatever I do to the left, I do to the right. Okay, good. Well, let's give it a try. I probably have a couple examples here to get us thinking in the right direction. It looks like I've got just under example 2, the first type right here, nice and straightforward. And then, as you can see, a couple of the second type just give us a little practice on that. Shouldn't be too bad. So I'm going to go ahead and actually rewrite this. And you don't have to if you don't want to. And if you can find a couple other ways to pull this off. Sometimes, you know, I'm a very visual person. Sometimes it just helps me with the symmetry there, putting the 2 over 1. Again, it's not mandatory by any means. If you don't feel it necessary, then don't even bother. But basically, this would be one rational expression set equal to another. And guys, we would cross multiply here. So let's knock this out fairly fast. Everyone cross multiply. Top left and bottom right. 3x times 1 is 3x. And then top right and bottom left, so 2 times x minus 1. If it's all right with you, I'm just going to go ahead and do is 2x minus 2 and remove the parentheses right away. Subtract the 2x on both sides. Do that relatively fast right here. And I get my 1x, and looks like negative 2. And I think that's good. I think that's going to be our winner. What we need to do, though, is be just a touch careful, because when I do cross multiply, I basically change the conditions of the equation. I change its form, don't I? Here was a good-looking rational equation. When I cross multiply, I created a nice linear equation. So even though this negative 2 works beautifully in this linear equation, I do need to go back and make sure that it does work in that rational equation that we started with. So I'm going to go ahead and take that negative 2 and put it back in just for my purposes here. Also want to make sure we did it correctly. 3 times negative 2 is negative 6. Negative 2 minus 1 is negative 3. And of course, that is equal to 2. So the first type, really not too bad. Please check in with me if you have any issues on that. What I'd like to do then is focus our attention on the second type with example 2b and c. And so again, I'm going to rewrite it, and you don't have to if you don't want to. I just want a little more room to work with here. So I've got this piece right here. And again, just kind of thinking off the cuff, I'm going to actually write that in factored form, and that should be x plus 5, x minus 2. Again, just might be helpful to go ahead and do that. And if you look at this, essentially what I want to do is eliminate the fraction component to this equation. And what that means basically is cleaning out all the denominators, 1, 2, 3 denominators right here. And so in order to do that, what we're going to do is very simply multiply each fraction by the LCD, each side of the equation essentially. And so I'm hoping you would agree with me that the LCD is going to be that x plus 5 and x minus 2. So that's exactly what I'm going to do here. I'm going to take the left-hand side and I'm going to multiply it by the LCD. I'm going to take the right-hand side. Again, got to keep it in balance. That's why we can do it. And I'm going to multiply by the LCD. And so what we're going to do is really distribute this in. This comes in right here, and then here is really the distribution once and then twice right here. And then it should, if we played our cards right, it should clean out all the denominators for this equation. So let's do it. I guess I would ask you this, of course. When we multiply it into this fraction right here, what does happen with the x minus 2's, one on top and one on bottom? They do cancel. And so I hope you see that we have the x plus 5 times the 4 again. Those cancel. And so I do get, I'm going to just do it as 4x plus 20. I hope you're okay with me distributing the 4 into the x plus 5. All right. Next course is to do the right-hand side. This goes into this fraction first and then this fraction second. When it goes into this fraction, think about this. I have the x plus 5 on the bottom, the x plus 5 up here on the top, and they should cancel. And again, that was our whole point, to get rid of this. So I end up getting negative 3 and times the x minus 2. And again, if it's okay with you, I'm going to do that as negative 3x plus 6. All right, and then here, what happens? This distributes into this third fraction, basically, the second one on the right side. What happens to the x plus 5s, everyone? What happens to the x minus 2s, everyone? And all I'm left with, obviously, when all that cancels out, is just the 7. And so then we get that piece right there. And again, notice how nice that is. we changed it from this heavy-duty rational equation to just a basic linear equation right here. So guys, let's bring the 3x on over. I'm going to subtract the 22. If it's all right with you. And again, just you're more than welcome to play around with this a little bit. But basically, I should get the 4x and 3x give us the 7x. These cancel. These cancel right here. And it looks like I have a 13 minus the 20. So looks like a negative 7 on that. And as a result, hopefully you see that x would be negative 1. Nice. And again, we do have to be just a touch careful because we did change the conditions of the problem. Here, not a big deal, but we got to make sure, is it okay for x to be negative 1 here? Yeah. Here, yes. And here, yes. So that is our solution set right there. All right, great. I'll go ahead and box up that other one just while I'm thinking about it. And that's looking pretty good. Let's go try letter C. Again, I'm going to rewrite just to have a little more room around it. You don't have to if you don't want to. I'm going to put the 2 over 1 as well. It just helps me. So notice basically 3 fractions then. Again, rather than combining together and then cross-multiplying, I'm going to get rid of the fractions all in one shot by multiplying by the LCD. And so in this case, 3 denominators, 1, 2, 3. And I'm hoping you see that the LCD here would just be that x minus 1. So I'm going to go ahead and multiply the left side by x minus 1. And then I'm going to multiply the right side by x minus 1. That keeps it in balance, exactly what we want. This will distribute in on the left side once and then twice. So just make sure you see what happens when we do that. And let's see it all unfold. All right, first one. It goes right in here. And the whole point of doing this was to get rid of that x minus 1, and I'm hoping you see that would do it. These are going to cancel, and it looks like I just get a 3x right there. When I distribute this in, obviously nothing cancels because this is just over 1, but basically I should get a 2 times x minus 1 there. And again, if you're okay, I'm going to go ahead and distribute that in. So this would be 2x minus 2. So again, it goes in here, cancel, just get 3x. It goes in here, 2x minus 2. Now I get my equals, of course. Sorry about that. In this case, when I go ahead and do it on the right-hand side, the x minus 1's cancel, and I just get my 3. And you can see pretty fast right here, the 3x and 2x make the 5x, and then minus 2, let's go ahead and add 2 to both sides there, and 5x equals 5, x equals 1, and it's looking pretty good. Now here's the thing on this one. Before I box this up, again, make the check. So x is 1 at this point. Look at what happens though when I try to put it back in the equation right here. I get 3 times 1 on top divided by, and here's the trouble, 1 minus 1 on the bottom. So in reality, even though this 1 works beautifully right in here, if you remember we called this an extraneous solution, unfortunately this does not work in the original. And so as a result, that goes away, and there are no solutions to this equation. So again, just make sure you check on these. Always want to make sure that it fits in what we would call the domain. So basically it really has to work where we wouldn't be dividing by 0. Has to meet our conditions of a rational expression, and now in the context of a rational equation. All right, very cool. So those are just the 2 types that we'll see. I think we'll try just a couple applications for the rest of the way here. And so let's go ahead and flip this over and see what we can do. So just at the top of your, the back side of your sheet, it should say something like a couple of applications using rational equations. And the first one is what is called job sharing. And this is a fairly common problem on those standardized tests. And I'll bet you saw this in some way, shape, or form in Advanced Algebra 1. So here's how I kind of do it. And if you did it in a slightly different way in Algebra 1, that's perfectly fine. You're more than welcome to kind of take a look at it from that perspective. They're basically the same. So let me just read a few things on here. We'll do an example to kind of get this going. And I broke it down as much as I could, get us thinking about it, try to kind of convince you that this is really how it's going to develop. So here's how I do it. It's helpful to think of the amount of the job, so what we're going to do in terms of the job sharing, the amount of the job completed in one particular unit of time. So if it's given in hours, we'll talk about it in an hour. If the job is given in minutes, we'll talk about it in just 1 minute, et cetera, et cetera. So 1 unit of time. So the example 3, it says, 2 pumps are available for filling a gas storage tank. Pump A used alone can fill the tank in 3 hours. Pump B used alone can fill the tank in 4 hours. If both pumps are used simultaneously, how long will it take to fill the tank? All right, very nice. I'll probably draw a couple diagrams with this, but just in essence, I've got a tank right here. Here's pump A, able to do it in 3 hours. Here's pump B, able to do it in 4 hours. If they work together, again, if they share the job, hence the name of this type of application, how long would it take to do it? All right, very cool. So let's go ahead and answer a few things. Just A, B, and C really go together nicely and very straightforward to get us going here. And then we'll see if we can kind of take a turn and see if we can set up an equation for this. All right, so here we go. Letter A. How long does it take pump A to complete the job? Well, 3 hours, given in the problem. How long does it take pump B to complete the job? All right, 4 hours, given in the problem. How long would it take both pumps to complete the job? Well, obviously, guys, if you look, that's exactly what we're trying to find. So in essence, that's going to be our variables. Typically, you see this in T for time, but if you want to go X on it, you're more than welcome to. Makes no difference. But for right now, I'm just going to say T hours. I have no idea. Obviously, that's what I'm going to try to solve for, and so as a result, I'm going to represent that with a variable. All right, so just in terms of the time component, we've got this. Now, obviously, there's not an equation that we can create with this. It's not like I can say 3 hours and 4 hours added together would be the number of hours that the pumps would take together. That doesn't make any sense, unfortunately. So the time components really don't produce any type of equation. So what we're going to do is the little strategy that I wrote above. So it says, let's investigate the amount of completion in 1 unit of time. In this case, 1 hour. So I'm going to draw my little tank off to the side again. And here's pump A coming in. And so let's read letter D on your paper. It says, how much of the job would pump A complete in just 1 single hour? So look at the information that was given about pump A. If you start your stopwatch and then stop the stopwatch an hour later, how much of the tank would be filled? And I'm hoping you would agree that it would be 1/3 of the tank. So with a 1/3 of the job can be done in an hour. Okay, 3 hours to complete it. As a result, in an hour, it can do 1/3. So something like this, 1/3 give or take. All right, nice. There we go. So pump A has filled up that much in an hour. All right, again, start your stopwatch and then stop your stopwatch 1 hour later. How much of the job would pump B complete in 1 hour? Well, it took 4 hours. So in a single hour, pump B could do 1/4 of the job. So basically what we're going to do here is take pump B, which is right here, and we're going to add another 1/4 of it. Something like this, give or take. All right, I hope everyone's okay with that piece. Trying to put a little visual on here. So pump A can do 1/3 of the job in the hour. Pump B can do 1/4 of the job in the hour. Now everyone, look very quickly, if you would, at the relationship between what we said in terms of the time, 3 hours and 4 hours, and the amount that they could do in a single hour. So if it took 3 hours, it's 1/3 of the job they can do in an hour. Pump B can do it in 4 hours, and so as a result, everybody, they can do 1/4 of the job in an hour. Everyone okay with that? This is just the reciprocal of the time. Cool, because in my opinion, it all comes down to representing this. So as a result, it says how much of the job would both pumps complete in 1 hour if they worked together? So remember, it takes T hours to do the job. And that obviously is what we're going to try to find. But in this case, in 1 hour, how much could they do together? Well, as we saw, everyone, this is the reciprocal of 3 hours. This is the reciprocal of 4 hours. So what we want is the reciprocal of T hours. In 1 hour, they can do 1 over T of the job. That's what I would put in. All right, just take a moment and kind of process that piece if you would. Okay? And now let's move to letter G. And so if you look at letter G, it says, if we added the amounts from part D and part E. So here we go, guys. This is how much A could do in the hour. This is how much B could do in the hour. If we added those together, isn't that how much they could do together in the same hour? And the answer would be yes. So this expression right here combined together would be equal to this right here. So I'm going to throw a little yes in right here, and as a result, we have an equation. So pump A can do 1/3 of the job in the hour. Add pump B's contribution, it can do 1/4 of a job in the hour. And as a result, that's equal to them working together, and in an hour, they can do 1 over T of the job. And that's how it works. Again, there is a slight variation of this equation. If you remember that variation and you want to use it, of course, please do so. But notice, rational equation, I do have 3 denominators here. And just to get everything rolling here, I'm going to go ahead and give us the LCD. LCD of 3, 4, and T would be 12T. Got that and got that. Let's multiply it in. 12 over 3 kind of cancels to 4. Hope you're all right with me saying that's a 4T right there. Distribute this in here. 12 over 4 is really 3. So that would cancel this out as a 3 and then the T. So a 3T right here. Here, guys, the T's cancel out. Looking at the right-hand side, 1 times 12 is 12. 7T equals 12. And lo and behold, I would get 12/7 hours solving for T. So even though we kind of wrote it like this right here, which I like, again, I think that was a good necessity, ultimately, we solved for our variable that we originally designated. How many hours would it take for them working together? 12/7 hours. 1 5/7. Cool. So take a look at that. And again, if you have any questions on that piece, please don't hesitate to ask. But as I said, just kind of a fairly common problem that works out pretty well this way. And if you have that perspective, in a single unit of time, how much can each one do independently? That's the same as they can do working together. Cool. All right. On to just the next piece. So we'll be talking about what are called parallel circuits. There are 2 types of circuits here, but this one in particular works well with this family of equations. So they're called series circuits and parallel circuits. And in this case, in a parallel circuit, the electrical current to each resistor, such as a light bulb, in the circuit is separate. So if this one was to burn out, the others would still have power. The most prevalent example of parallel circuits is probably Christmas lights. So if one bulb burns out, it doesn't affect the electricity going to the other bulbs. So parallel circuit, again, so it's kind of separate there. And as a result, if one loses power, the others do not. All right, a little picture, a couple things, and let's just read it and then do our math behind it. So there are 2 scientific principles that we're going to deal with in the parallel circuit. The first one is what's going to be referred to as the current. Sorry about that. Didn't mean to cancel that out there, so just underline. So the total current. So the total current, which we would designate as I, is very simply equal to the sum of the currents through the individual components. So this plus this plus this plus this equals the total current. No big deal. As a matter of fact, we probably won't even do an example with that. What we will talk about is the resistance in each. And so here's the principle that we will utilize. And it says the reciprocal of the total resistance, so slightly different here than current, so a different measurement when dealing with circuitry. So the reciprocal of the total resistance of all the components is equal to the sum of the reciprocals of the resistances of the individual components. And of course, I kind of illustrated that below right here. So R is going to be the total resistance. And so it's the reciprocal of the total resistance, so 1 over R. And then here would be the individual resistances, R1, R2, and R3. So the reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances. Okay, and what is resistance? I'll just read what we have on the paper here, and then we'll go ahead and do the two examples. Resistance is a measurement of how difficult, so resistance, great word for it, of course, is of how difficult it is to push electricity through a circuit. Factors that can affect resistance are the size of the cross-section of the wire, the length of the wire, the material of the wire, etc., etc., etc. So how difficult it is to get electricity through the circuit. That's the resistance. And in terms of the components, again, the sum of the reciprocals of the individuals is equal to the reciprocal of the total. All right. Well, let's go ahead and try it out there with just a couple. And so examples 4 and 5. Number 4, the total resistance in a parallel circuit is 625 ohms. If two of the resistors are 2,000 ohms and 1,000 ohms, determine the resistance of the third. All right, very nice. So total, guys, is 625. So the reciprocal of the total, there it is, reciprocal of the total, is equal to the sum of the reciprocals of the individuals. So one resistor has a resistance of 2,000, so 1 over 2,000. The second resistor has a resistance of 1,000 ohms, so plus 1 over 1,000. Again, sum of the reciprocals. And then plus the third resistance is unknown of the third resistor, so I'm going to go ahead and just call that R. And obviously the reciprocal of R would be 1 over R, so there you have it. All right, very cool. And you can see it's just a rational expression, type 2 here. I'm going to get the ball rolling for us, hopefully have my information right here. But basically, I think what we're going to want to do is multiply everything by the LCD. And again, just to kind of get you rolling on this, let me give you the LCD. It would be 10,000, numerically by the way, so 10,000 R, as a matter of fact. So same deal over here, guys, 10,000 R. And that's what we'll go ahead and multiply in. I like this little shortcut method dealing with these rational equations. It works pretty well. I've got some information on my paper here, so I'm going to just kind of relay it to you and put this in. If you want to do some calculations as well, wouldn't be a bad idea. So guys, I have the 10,000 R times 1 over 625. If you were to do 10,000 divided by 625 on your paper there, on your calculator, excuse me, and then write it on your paper, I believe we get 16. So this is 16 times R times 1. I'm getting a 16R on that, basically. That's what I'm trying to find. And then in this case, let's see. Oh, that's an equals. Sorry about that. Let's get that. And so equals, and then let's do the same thing here. 10,000 R times 1 over 2,000. Now let's distribute. 10,000 divided by 2,000 is 5. So it looks like a 5R right here. Repeat, of course. Do it in here, and 10,000 divided by 1,000 is 10, so 10R. And then R's cancel here, and I end up getting 10,000. Interesting. Okay, great. Well, guys, combine those together. 15R over here. Subtract that on over, and so 16R minus the 15R. And I think we get the resistance on this is going to be 10,000. And looks like I have a little spot for it over here. If you want to go ahead and solve it in a little more detail, write out a few more steps, you're more than welcome to. But I'm getting that as the resistance on the third. All right, very cool. So just forming a type 2 rational equation on this. Nice. Hey, last one here. Let's try it out. Example 5. In a parallel circuit, each of 4 components has a resistance of 750 ohms. Determine the total resistance. All right, great. So the sum of the reciprocals of the individuals, and each one happens to be 750. So there we go. I've got 4 of these. Each resistance is 750. And that's equal to the reciprocal of the total, and that's unknown. And again, if you want to use a different variable on this, if this capital R is throwing you off, please, put a little x in there. You know, we're trying to find the total resistance, and so, you know, any variable would do. Theoretically, this is kind of an interesting one as I'm looking at it. You could do an LCD, which is going to be 750R. You know, that's not a bad idea. You could probably do that pretty fast. I see this working really nicely. You know what strikes me? And again, it's just my perspective, so if you have a different one, please go with it. But it looks like I can combine those incredibly fast. They all have the same denominator, and so let's just combine the numerators. Isn't that just 4 over 750? And then 1 over r? Something like that? And then you can kind of see a little cross multiplying in there. 4r is equal to 750. You know, it's really just going to work out pretty nicely here. Divide by the 4, and I'm getting about 187.5. And I'll put that in the blank as well. So 187.5 ohms. Again, if you have a slightly different approach on that, please, you know, utilize it. But I think regardless, we'll probably end up in the same position here. And it looks like it's just going to be the reciprocal of this piece right here. Nice, great problem. So we did just some good algebra in this family of equations, did a couple applications with them. Yeah, some really nice math with that. All right, we'll try some practice problems if you get an opportunity, of course, and let me know if you have any questions on it.